In this paper, we present a direct shape optimization method to strengthen 3D printable objects. Many applications in 3D printing require the design of 3D shapes to bear significant external forces. Given an input shape such as this chair model, our goal is to optimize the shape until it can withstand the required external force, while remaining similar to the input shape. Here the red color indicates the region and direction of the external force, and the green boundary indicates the surface that should remain fixed. Our algorithm generates an optimized shape that's similar to the input but can withstand 3 times as much force as the maximum allowed on the input. The silhouette image here shows the difference between the original shape, marked gray, and the optimized shape, marked purple. Here is another example where the input shape is a table and the external force is applied uniformly from the top. Our optimized shape, shown on the right, can again withstand 3 times as much force. Here is the silhouette image that shows the difference between the input and the optimized shape. Our algorithm operates directly on the input mesh. We perform physics simulation and shape optimization in a unified framework, where the physics simulator is an integral part of the optimizer. Given an input shape, our algorithm iteratively updates the shape and its deformation due to the external forces and boundary condition. Specifically, we solve a linear system that minimizes an objective function under geometric and simulation constraints, which are formulated as equality constraints. The system is solved over many iterations until the result converges with the equality constraints satisfied. We then check if the von Mises stress at each vertex is below the material's yield strength. This requirement is represented by inequality constraints. If the inequality constraints are not satisfied, we increase a penalty term in the objective function and repeat the computation. This continues until our method converges to an output shape where the stress at each point is below the required threshold. Therefore, all constraints are satisfied. Now we show some experimental results. We start by demonstrating the effects of several constraints. First, we detect symmetries in the original shape and incorporate them as part of the geometric constraints. Without symmetry constraints, the optimizer can deform the shape asymmetrically, which is not ideal. By adding such constraints, the optimized shape remains symmetric. To preserve the surface appearance of the original shape, our objective function includes an extrinsic distance term, which ensures the optimized shape does not deviate significantly from the original shape in Euclidean space, as well as an intrinsic distance term, which compares differential surface properties and ensures the surface details and smoothness are preserved. Including both terms is critical at keeping the result geometrically similar to the original shape. Next, we show user-defined constraints, which incorporate users' preferences on how the object will be used. Here, the second image shows an optimized stool model where the top surface is no longer flat. This can be addressed by adding user-defined constraints that forces the top surface to remain flat during optimization. We have applied our algorithm on several furniture and utility models. The detailed results can be found in the paper. In the following, we show a few animations that illustrate how each original shape is deformed into the optimized shape. Finally, we have performed the physical validations using printed objects and a professional force gauge. For details, please refer to the paper. This concludes the video. Thanks for watching.